after having considered the conditional family, we are now in a position to move into the marginal family. We already saw that in the conditional family we have options. For example, the Cox model, the multivariate exponential family model, is more useful in case we have, let's say, for example, correlated hierarchical data but not organized longitudinally. The transitional model or the autoregressive model is very important in contexts where we have longitudinal data, because there we can make use of the natural ordering of measurements within a sequence over time. And it's needless to say that they also play a very important role in time series, but that's outside of the context of this course. In marginal models, we will have way more options insofar that the next few chapters are devoted to marginal models within the rest of the part, and not only this chapter number 19. So, to set the scene a little bit, the first thing we have to do with a marginal model is, well, build it up from the ground. We have no device like a dependence on the previous outcome, or later a random effect that immediately sweeps through the correlation and has the whole model specified. No, if we model, for example, the marginal mean function, if we write down a logistic formulation, for example, the probability of a severe infection at a given time, fine, but we don't know yet the association. So then we need to think about what association function are we going to use. And when we have that in place, we may say, hey, but this is the pairwise association. What about the three-way association, right? Think of the conditional model that we specified earlier. We had main effects, theta ij. We had pairwise interactions, theta ijk, then theta ijkl, etc. Something similar will happen here. A bit like in the toenail data set, we can start by saying, okay, when we have one link function, we have 7 link functions. So specifying the marginal mean function is usually not too much of a problem. So specifying the marginal mean function is not a problem at all. We have specified that before. It specifies the mean vector. It specifies also, therefore, the relationship of the mean function to the through the link function with covariates. So to clarify that a little further, we are going to go and look at our piece of paper again, where we wrote down the function a short while ago. So, remember that we had, we make that a little brighter, we had, for example, in the toenail data set, treatment, time, treatment by time interaction. This is our 7 mean functions. What is circled here is the 7 mean functions. Why 7? Well, you just let t take values 0, 1, 2, 3, 6, 9, 12, and we have all of them. That's all it takes. So that specifies the means. I can write it next to it and say it again. This is the 7 means. And I can combine them into the mean vector. The covariates here are time, their treatment, and treatment by time. So that's the design matrix X. We build it up from there, fine, no problem at all. And then, as we said, these means still are going to specify all the variances as well. Mean times 1 minus mean is the variances. These follow very easily as well. They're here, so these are the variances. But what with the correlation? That is an unknown new set of parameters we have to think about. So to back up a little bit, what I wrote down for the toenail data set, in general you can say, is the logit link. We have the means and we link the means to a linear predictor function through the logit link. Or if you wish, you can use the probit link, the complementary log-log link, all the link functions that are mentioned, some of which are used in some examples, etc. And then we go to the association. What Ekholm a long time ago proposed was the so-called success probability. And the success probability is, wait a minute, you can work with a logit link because you have a probability. But the pairwise success probability, remember this, the pairwise success probability is the probability that Yij and Yik at the same time are equal to 1. In other words, mu ijk again. That success probability is also lying between 0 and 1, so why not applying a logit there? There are serious problems with it, because if you say the pairwise success probability is written as a function, a logit function, so it will become a linear predictor, there will be a linear predictor, a simple function of covariates. You have that for the pairwise successes, you have it for the first marginal mean, you have it for the second marginal mean, but there are 3 other functions as well. That is, you have the pairwise failure probability, failure at time 1, failure at time 2. These 3 pairs will have a very messy function, and worse of all, they may sometimes end up outside of the unit interval. So the success probability approach has been met with question marks. The marginal correlation coefficient, well, I think I don't have to explain a correlation function at this moment. So the marginal correlation function takes this form. And again, you can see it's a transformation of the univariate means together with the pairwise means into a new correlation parameter. Correlation lies between 0 and 1, at least it should be. This is why we don't transform it with the logit link. This is just the definition. So is the value, the rho, the correlation that a priori is going to be somewhere between -1 and +1. People have used the Fisher-Z transform to make sure that it takes values on the entire real line. Just as a side remark, the Fisher-Z transform is nothing but a logit transform, but starting from a different interval. The logit maps the unit interval on the real line. Fisher-Z transform maps the -1 +1 interval until the entire real line. But other than that, they're actually exactly the same. Okay. A third approach is the marginal odds ratio, where you, and it's easiest to understand it in this form, where you have the pairwise success probability multiplied with the pairwise failure probabilities. In other words, the discordant ones divided by the concordant ones, I should say, concordant ones divided by the discordant ones. It's very intuitive, very appealing. It follows straight from a 2-by-2 table where you take the diagonal multiplication divided by the off-diagonal product. And also there we have a value that lies between 0 and +infinity, so here the log link would be a very natural link. In all cases, higher orders can be defined similarly, but if you go for a fully specified marginal model, you have to do that. You have to specify the higher orders. Okay, let me give you an example with the Bahadur model. In the Bahadur model, we start from the univariate probability, so univariate logistic regression. Think again, think back of the toenail data set. Then we have the pairwise probabilities, mu ijk or pi ijk. You know that here I'm using pi and mu interchangeably. The correlation is given here as well, the pairwise correlation. And from those, I can now say, hey, wait a minute, if the correlation is given as a function of pi, just as well can I turn it around and solve this for pi ij, and then I get pi ij as a function of the correlation, given the univariate probabilities. Now, that is for 2 times, but we may have 7 or 10 or 15 times. Well, you can also do that using the following devices. Start from the standardized residuals. Call it Pearson residuals if you wish. The stochastic one is circled now, and I put in a box the data realized version of it. Rho ijk, well, the expectation of residuals, if all goes well, is equal to 0. But expectations of cross products is equal to pairwise correlations, at least if it's a cross product with 2 terms. A cross product with 3 terms produces the 3-way correlation. And hey, that's interesting, a 3-way correlation. Is there even something like that? In the normal case, for continuous outcomes, we usually don't think about. And we don't have to, because in the normal distribution, the mean and the variance specifies all higher order moments. But not, even not in the simple case of a 2 by 2 by 2 table. If I give you the pairwise association parameters, the marginal means, you have 6 parameters, but there are 7 free parameters, it's still underspecified. So for binary data with increasing size, the number of parameters is, and I visited that issue already, is of an exponential magnitude, 2 to the power n minus 1. Whereas fortunately in the Gaussian case, and that's a very fortunate thing also for the linear mixed model, there I have means, and the means is in length linear in the size of the data vector. I have the variance-covariance matrix, which is quadratic in the size of the data vector, and that's it. So it's going to increase, and it has to increase, and one way to make that happen is by 3-way and higher order correlations. Oh boy, what kind of model is that going to produce? Well, the model is actually not so very difficult. We can say it's just a product of 2 factors. The first factor being nothing but logistic contributions, or binomial contributions, or Bernoulli contributions, if you want to call it that way, pi to the power success times 1 minus pi to the power failure. And then you have a correlation function. And that correlation function here takes a simple form, 1 plus something. Now look at the something. The something is equal to 0 if all correlations are equal to 0, and then C is equal to 1. So in that case, the model reduces to logistic regressions. Once again, something that reduces to logistic regression. And these correlations, of course, if they're going to be different from 0, anything goes. I will get an upward or a downward correction. I could, for example, also here say, let me restrict things to just the pairwise associations. The model would simplify a little bit, but it may or may not work in practice, of course. And then the probit model. I'm going to introduce the probit model not in formulas, but actually in terms of a graphical display. If I think about univariate binary data, I can think of them arising from an underlying continuum. So I have an underlying continuum. Think of a normal variable. Think of a logistic variable, which has a very similar shape. And then you say, I create a cutoff. Everything that falls to the left, I call a failure. Everything to the right is a success. For example, body mass index can be categorized into non-obese and obese. And there it's very explicit because you would be doing it. But even if it's not explicit, you can think about it implicitly and say every binary variable can be thought of as arising of an underlying continuum which integrates to 1 overall, which means the moment I divide that into 2 pieces, I split that. I split the total probability into a failure and a success probability. It always works. And if you use an underlying normal distribution, then this model is called the probit model, the classical univariate probit model. Now we said earlier, if you have a univariate probit, you can a univariate normal, you can easily generalize it to a multivariate normal and do the same thing. So think of this space now as being bivariate and filled with a bivariate normal distribution. You dichotomize. And for example, if I dichotomize, I can say by doing just that, everything here is a double success. Everything here is a double failure, etc. Or I can do what I actually do on the graph and say, let me apply that for a 4 by 3 outcome. So 2 variables, one with 4 categories, well, then you dichotomize, or you actually tri- or quadrichotomize into 4 categories. In one direction and in the other direction too. So you get 3 by 4, a 3 by 4 grid, and the probability mass in each one of those rectangles, some of which are open, infinitely large, that mass is the corresponding probability. The advantage of using an underlying probit model is a multivariate normal comes with correlations. Those correlations are pairwise correlations, and that's it. So the Bahadur model needs higher order correlations. The probit model only needs pairwise correlations. It looks like these two models are similar, are they not? Well, to see that, let me analyze a data set. And this is one of the ad hoc data sets that I will be using here and here only. It's a relatively old study right now, the POP study, Project on Preterm and Small for Gestational Age Children. So it's children born in the Netherlands in 1983, 1530, which is a good large fraction of children with either small gestational age or children that are preterm. The data that we have is twofold. There is perinatal information, so around the time of birth, bilirubin, the substance that makes children yellow if it's too high in concentration, whether or not there are neonatal seizures, and whether or not there are congenital malformations. Okay. And then 2 years later, there are 3 ability scores. And these ability scores assess whether the child is evolving normally. Are the movements normal? Can the child pile 3 bricks, yes or no? And these are assessed by a physician. And then if the child is asked to do so and given a ball, is it able to put that ball in a box? Okay. Now, a child would be normal if it scores positively on all 3. And this is an interesting case of why we would do longitudinal or multivariate modeling. We are actually interested, maybe not so much in the correlation, but we are interested in what we call the joint probabilities, the union probabilities. So I could build a logistic regression for each of the 3 outcomes separately, and then multiply the result and say, this is the joint probability, but no. If there is positive or negative correlation, I may be underestimating or overestimating the probability. So the probability that ability score 1 and ability score 2 and ability score 3 is equal to 1, to model that properly, I need a proper trivariate model. I need to take the correlation into account even when I don't care. Okay, so let me apply the Bahadur model. Let me apply the probit model, and let me apply the Dale model. Now, I've introduced these models to various degrees of detail. The Bahadur model, there you saw the explicit expression. For the probit model, you saw the graph. And now for the Dale model, I can say it's actually similar. The only thing we are going to do different here is we are not assuming an underlying normal distribution. We're assuming an underlying placket distribution. To put that in more simple terms, you say, okay, let's just assume that marginally I have logistic regressions in both dimensions. I have logistic regressions. And then the association is determined as follows. I take a grid point wherever I want, here for example. And then I calculate the probability mass in each one of the 4 quadrants. 1, 2, 3, 4. I calculate the cross ratio and I keep it constant wherever I put the dichotomization. So I make this point travel through the entire space. By making it travel, I still keep the odds ratio constant because it's an odds ratio. That is the Dale model. Brief, the probit model and the Dale model are both models based on an underlying continuum that I seem to discretize. The Bahadur model starts with underlying logits. The Dale model, I can couple to logits, but I can also couple marginally to probits, to normal distribution. So in other words, the middle models have a normal underlying variable, so they are actually probit regressions. The outer ones are logistic regressions. Well, first and foremost, the coefficients are everywhere significant. Wherever I look, in each one of the three outcomes, the first ability score, the second, and the third. Yes, and they're actually very similar between Bahadur and Dale. They're also very similar between the probit and the Dale with normal, and that's of course to be expected. But they're also similar if I compare all of them, because we know that logistic regression and probit regression are connected through the scale factor pi squared divided by 3, of which I take the square root. So it really doesn't matter so much right now. Let's look at the association, and for the association it's a little different. The Dale model uses odds ratios, we see that here with psi. The Bahadur and the probit model, they use correlations. Let's first look at the Dale model. We know that we can use probit regression, Dale normal, or we can use logistic regression, Dale logistic. But in both cases, as I just said, we use the odds ratios as association. Well, the odds ratio is a little bit more difficult to interpret than a correlation because it's unbounded. If you have positive association, the odds ratio can really go to infinity. So 17 is large, 30 is large, 17 is large, but how large is that? We also have a three-way association in this case, and that turns out to be non-significant. But we do have significant association. So much is clear. For correlation, the probit model, start there, also gives a very strong correlation. But hey, wait a minute, in the Bahadur model, the correlations are much smaller. And we see a very interesting phenomenon. 0.27 and 0.73, they sum to 1. It makes some people think, hey, is the Bahadur and the probit model somehow complementary? Nonsense, nothing of that. This is pure coincidence. It doesn't happen here, it doesn't happen there. But what we do see is the Bahadur model estimates the correlation much lower than the probit model. And they both feature the correlation, yes, but they're not the same correlation. In psychometrics, people would call the Bahadur correlations manifest. These correlations were introduced, remember the Bahadur model, without any use of an underlying variable. We just do it on its own terms. We build a logistic regression, and then we have the correlations directly of the binary outcomes. The probit model has correlations of the underlying bivariate or multivariate normal variable. That means we assume that the variable we observe is a dichotomization, a discretization of an underlying continuum, and in that underlying continuum there are several variables also, and they are correlated with each other, and that's a different thing. So it's indirect. That's an indirect correlation, and if we use that, we use these correlations as an approximation to those correlations, we are wrong. We completely underestimate the correlation indeed. Okay, the three-way correlations, that's also interesting. In the Bahadur model, it was set equal to 0 for simplicity, so that's a choice that we make. In the probit model, it's simply not there, because the probit model is, again, that underlying multivariate normal, remember? In this case, it's an underlying trivariate normal, so there is no three-way correlation that is different from two-way correlations. That's a different story. All right. Where does that leave us? It leaves us to the end of it brings us to the end of the model family marginal, where we have fully specified models, but we feel, first, there are many options. Second, it may well be fairly complicated to apply these methods when you have 4, 5, 6, 7, 8, more and more variables, repeated measures available. And think back of the toenail data set. In the toenail data set, I wouldn't want to deal with all these higher order correlations. What I want to do there is I want to make inferences about beta 3 is equal to 0. And that will then lead me into generalized estimating equations.